This video focuses on the use of a widely available Mathematica notebook introduced in the video prior to this one, and it's used to plot the geodesics followed by a massive free particle in the equatorial plane of a Kerr black hole. Now, this notebook can be found here at this link. It can be found at many other locations on the web too. It's a wonderful package. It goes with an excellent textbook, really a fantastic textbook, this one. And the notebook itself is a beautiful piece of work. And with some modification, it can be made to plot the geodesics in the equatorial plane for Kerr black holes. It was originally written for the Schwarzschild black hole, but by modifying it, you can make it work for the Kerr black hole as well. So it's a beautiful piece of notebook, and I introduced that in the last video and showed it briefly too, but now I'll just spend a few more minutes to show it to you in a bit more detail. All right, so in the last video, we looked at the Mathematica notebook with some modifications. I went through what those modifications were and then used that to produce a parametric plot of the geodesics followed by a free massive particle in the equatorial plane of the Kerr black hole. So the effective potential used was this one. How I derived that's all in the previous video. The integrand was this one, this object here on the right. We use that to, and then we use a notebook to integrate this integrand here. How I've arrived at this, it's all in the previous video. Okay, so let's have a look at the notebook itself. And as I said, it was written for Schwarzschild geometry, but with modifications, it can handle the Kerr case. Now, in the previous video, we finished with this plunge orbit. That was the one I showed you briefly. I'd like to show you something a bit different now. I'm going to go and look at a bound orbit. And so let me check out the information I need. I'll keep these units for one, but we can put back the actual units for these and plot it as well, but then you have to change the angular momentum and the energy parameter as well to appropriate values. Okay, so the stationary limit surface is 2 lots of gm on c squared, which is just 2 in these units. Source mass m is set to 1, the gravitational constant set to 1, the speed of light set to 1. This is the dimensional spin parameter, which I'm thinking of a particular Kerr black hole, a quasar, a billion solar mass quasar. At the center of that is a black hole, billion solar masses. And its spin parameter, dimensional spin parameter is 0.74. I've used it in previous videos, so I tend to stick with that. Bit of a favorite of mine. Stationary limit surface, 2 lots in these units, 2 lots of gm on c squared, which is just 2 on the plots that you'll see below. The upper event horizon, the outer event horizon, this object here is about 1.67. Okay, and the reciprocal of that is 0.59, as I pointed out in the previous video. Okay, so here's our effective potential. All right. Now, all of these GMs and small m's are all going to be 1, and C will be 1. So angular momentum, 4.65 units, that's per unit of mass that we're talking about here, that we're plotting for. And when we plot the effective potential, we've got this. Okay, and I'm going to keep that 4.65 for this bound orbit I want to demonstrate. I looked at the derivative here. It tells us about the turning points on the plot here, where they are, and their value. Here I'm going to change the value of the energy. I'm going to make it negative, and I'm going to demonstrate a bound orbit, not a plunge orbit now. So, and I'm going to have, what was that, 0.2, wasn't it? No, it wasn't. No. I'm going to do 0.5. That one I think looks nicer. And I will be, so this orange line will drop down here just below the horizontal axis into the negative region, because it's negative 0.005. We'll plot that in a minute. Then we'll keep going down. I'm going to start from initial position of 200 gm on c squared. So it'll just be 200 in these units. And as I said, the original program was written as 1 times 10 to the minus 8. My enthusiasm changed it to 10 to the minus 9. Anyway, now, wonderful thing, this program, it tells you what type of orbit you're going to get, whether it is bound, scattering, start from fallback orbits, and plunge orbits. Now, if you remember, we finished last time with and here was the integrand, and we're going to numerically integrate that. This part here was concerned with how many orbits you've got. And don't forget, we're working not in spherical polar coordinates, but we're working in spheroidal coordinates. And so we must have, this is 1 on u, which is r squared. So this is the r squared, but in units of, in the variable u, plus a squared times the cos of the angle to give us each of the x and y values, okay, for each value of r. We set the orbit to 1. Anyway, last time we ended up with this plunge orbit, but what I'm going to do now is just briefly, here it is. I'm going to start off with 1 orbit. This is a bound orbit. That's n orbit 1 means 1 complete orbit. And we're going to evaluate the notebook. Yep. Let's just go down and check that everything's progressing all right. That's a bit, yep. Sometimes we have to do that twice. Make sure it evaluates properly. Okay, now we can go down. And I may have to evaluate again to make sure it gets the information. I don't know why it does that sometimes, but it can do. Okay, now the only thing is what I didn't change was I needed to change the plot range. I should have done that before starting this video. Let's see how we go. I'm starting further out, so as you can see, the event horizon here is about, that's 1, 2, 3, 4, 5 units. That's about 1.67 here. Blue edge just clearly marks the boundary. Okay, now it's getting better. Yes, look, it's all working nicely now. Sometimes when you first start it up, you've got to evaluate twice. I don't know why, but okay, let's go again now. Just asking the notebook to evaluate all that input, and we'll go right down the bottom. You just have to be a bit patient too. Takes just a little bit, not too long, but a little bit of time to calculate. And we shall have very shortly, we shall have a plot, a parametric plot in 2D, looking down from positive z, looking down. So here we're starting at about 200. Here we go like this. There we go. That's 1 orbit. What I'm going to do now is I'm going to change the number of orbits, and I'm going to go for, as soon as I find it, 2. I want 2 complete orbits. Okay, and again, just evaluate the notebook. It says energy E is the orange. It's just below the negative there, so we're going to have a bound orbit. If you notice here, the energy parameter is 0.005 negative. And you remember one of the approximations I made in the previous video was the energy over R. I said the R is generally about 2 units and greater, and the E value is very close to 0. So we made this approximation that E on R is approximately 0. So it was one of the approximations I made, the second approximation I think I made in deriving the integrand. So anyway, let's go down, let's have a look. Here we are. Just give it a little bit of time. Okay, as you can see, there's 2 complete orbits. And what we can do, you can see the precession that's occurring, but that'll become clear if I do n equals 3. I'll go back up here. I'm going to ask now for 3 complete orbits. And evaluate that. Come down here. Now it's just a matter of waiting as we come. It's a beautiful piece of work that's been put together by whoever, James Hartle or whoever created this notebook. Beautiful piece of work. And with modification, it can be extended to Kerr and other cases. We're just waiting now. Third orbit to come. It is just a matter of patience. As you can imagine, it's going to come around here and out here. It's just gone here to there, and then from there we go. And you see it's come around third orbit there. All right, there's many other types of orbits we could show. Basically categorize them into bound orbits, scattering if you like, fallback, and then plunge. I also changed this value here. There was 0.5 here. I changed that to 0.67 being the value for the Kerr, outer event horizon of the Kerr. 0.5 was a value that coincided with, the reciprocal of 0.5 is 2, so it coincided with the event horizon of the Schwarzschild black hole, but the Kerr black hole is inside that. The outer event horizon of the Kerr black hole is inside that Schwarzschild radius. So the Schwarzschild radius actually coincides with the stationary limit surface of the Kerr black hole. All right, so I've changed that from the Schwarzschild case. That was 0.5 there, and also this was 0.5. I changed that to again the 0.67. Let me see if there's anything else. I think there was up here somewhere. I can't remember where it was. One of those U values I altered. But anyway, there's a bit of change, but not a great deal. But also, I mean, you could play with these, and instead of setting C to 1, you could give it its original value. Same with G, M, A squared. Just means then you need to give appropriate values for the angular momentum here, because angular momentum numbers are quite high. They're quite large numbers, as you can imagine. So you think about R times MV, you can think about a number that would be quite high in reality when you think of all those meters involved. And you change E accordingly as well. See what you come up with. And then you could plot the actual case for that. I may yet do that, but I'm not sure. But I think possibly the next video, what I will look at is with this. Sorry, I'm scrolling all over the place here. But with this, I may look at, could I come up with another approximation for the integrand? So this bit down here, could I come up with an approximation that's closer to the original? So I made 3 approximations to arrive at this from the workings, as you saw in the previous video. And what I may do is try to look at, can I simplify that further, maybe use fewer approximations, or come in a slightly different way and see if I can produce a different integrand and improve on the result here. So that might come in future videos, but I'm not sure yet. All right, thank you everyone.